Anthony, Kevin, and Lyra, who will be giving some thoughts on vision. So Anthony, take it away.
All right. Hi, I'm Anthony Demetrescu. I'm a mentor on 3476. I've been a mentor for 4 years. I've been the lead. I was a member on Code Orange for 4 years, and I'm the lead programming mentor 4 years running. So I'm just going to walk you through how Code Orange does vision, and yeah. So first of all, the hardware, we use bright, very bright 1 watt LEDs using a constant current driver. We use a USB camera that's PCB mounted with interchangeable lenses for varying distance applications. We use a Jetson TX1 with an Orbity Carrier board to shrink its footprint down to something that we can actually fit on our robot. The Jetson Nano is cheaper and it has comparable performance, so that's an option if you're looking for that. All right, so overview of the vision pipeline. So obviously our camera transmits image data to the Jetson so that it can process the images, does that via USB. The Jetson then processes the images locally and then sends a very small amount of target data to the Roborio over UDP, which Ethernet and then Wi-Fi through the bridge. The Jetson also sends a live stream to the driver station for the drivers to use. And the Roborio can send camera exposure settings back to the Jetson via UDP. All right, so the first step in image processing on the Jetson is gross filtering. So the way we do all of these image processing steps using functions in OpenCV, which is an image processing library. So the first thing we do is we convert the image to an HSV image, hue, saturation, and value instead of RGB. So first of all, we want to threshold the image to only get the parts we care about. So because of our green LEDs, the target, the retroreflective target, is very bright and green. So we want to look for a green hue. We want to look for a very saturated color, so as opposed to gray. So very green as opposed to gray. And then a medium to high value because, again, it's very bright. The output to this is an image that's all 100% or all 0. It's a binary image. The next step we take is a morphology operator. So we use opening, which first gets rid of, shrinks all the white pixels in the image, and then expands them again. And this gets rid of little tiny granular noise. It's much faster than using a blur kernel, and so we can get rid of a lot of little tiny noise we don't want to deal with. The next step is target extraction. So we use another OpenCV function to find contours, which is the outlines of the various blobs in the image. And then we want to classify these. So we're going to calculate a number of different metrics about these blobs. We want to get rid of those that are clearly not the target. So we want to discriminate based on, aspect ratio, orientation, or if it's like incredibly small and it didn't get processed out by the morphology operators. If the target that you're actually looking for is multiple blobs, like in 2019, where it was these two rectangular bars that I've made a mock-up here, figure out which blobs can feasibly make a target. So, for example, the top one would be a correct target in 2019, and the bottom one would have been in between the targets, which is not a real target, but possibly a match. Once you're done with all that, you want to take the information you got from the Jetson and convert it into something that the Roborio can use. So we get the position of the center of the target relative to the camera center. We found it helpful to convert it to -1 to 1 instead of the pixels, which makes it easier to deal with resolution changes if you change out your camera or whatever. And then possibly estimate distance in the Jetson based on the area of the target. If it's a larger area, it's closer to you, or if it's a smaller area, it's farther away, or the angle of the target vertically and your robot's height, for example. You could make a mathematical model to figure that out. Then you want to use the target information. So on the Roborio, so you want to turn the camera position, that -1 to 1, into an angle using the field of view of the camera. And then you'd want to use the distance you calculated to make a decision, like for example when to score, or to compensate for the camera not being at the center of of rotation for your robot, whether that's a turret or your drive base center of rotation. So then you would want to find the location of the target in space based on the angle and the distance away from the camera, and then calculate where that is relative to the center and turn to point at it. The last thing we do is we stream, like I mentioned earlier, the vision stream to the driver station so that our drivers can make sure that the vision system's working. And then we also annotate it so that, again, they can see that it's working. We put distance on there and the center of the camera frame. And then you want to, what we've implemented is a way to change the exposure dynamically so that the operators can have a look through the vision camera at the normal exposure level, but then you can darken it down to a vision exposure level so that the target isn't so blown out and you can get better tracking. All right, so that's all I had to say about that. Our code is available on our GitHub, and you can take a look at our 2019 and 2020 vision repositories.
Up next, Kevin will share some of his thoughts. Yeah.
Okay, so my name is Kevin Jaget. Thanks everybody for coming out. I'm a mentor on Team 900. I've been on the team for about 6 years now, mainly mentoring software, but doing a little bit of everything, I think, just like most mentors. I put our support email on here in case you have questions after the presentation. This will go to me, most of the other mentors, and we can forward it to our students if you actually want the real information on how our code works. So what I wanted to do today was to give just a quick overview of what the zebracorns have been up to for the past year or so. I'm not going to go into too much detail on any particular subject, but feel free to ask questions. I'd be happy to discuss them here, or like I said, check out our email address if you want more detail and code. So kind of an outline, we've got some new hardware we're working with. We have some updates to our retroreflective tape targeting, and then we've been working with machine learning for object detection, and then I'm going to talk a little bit about how we use these results to automate our robot. So the hardware setup we're working with this year, we have a Jetson coprocessor, and this year we're using the Xavier NX, which is the latest iteration of the Jetson family. It's kind of like if you heard the Jetson Nano, it's about the same size, just a little bit faster, actually a lot faster. And like other teams, we use this to offload most of the compute-intensive operations off the Roborio and do them on something more, I don't know, better suited for vision processing. The other big hardware update we have this year is we've moved on to using the Stereolab Z2 camera. This is an RGB plus depth camera. So it's got two lenses, and it uses stereo vision to calculate distance to any pixel on the screen. And this is a real benefit because it lets us convert from the image coordinates into real-world XYZ displacements that we can use to drive the robot or target a turret with it. Our retroreflective tape targeting, it's actually very similar to the process Anthony was talking about. So I think a lot of teams have kind of figured out the right way to do this. Our code is also uses OpenCV. A couple of differences I will note. The first one I mentioned here, which is since we're using an RGB plus depth camera, we get an actual range to the target, which lets us convert to, like I mentioned, actual real-world coordinates we can use to drive the robot. The other difference we use is we have kind of a different way of filtering and finding green pixels. So instead of using HSV filtering, what we do is we take the red and blue pixel values of each pixel and add those together. And then we take the green value and subtract the red plus the blue from that. And what that does is for pixels that are only green, it gives a really high value. For pixels that have no green, so basically they're not reflecting any of the LED light, it's a very low value. And then the interesting part is if we have something that's got high red, green, and blue values, for example, white light, you can see the fluorescent lights up here at the top of our target. Those would get filtered out because the red plus blue component would kind of cancel out the green. So this is kind of a quick and dirty way to get a like a binary image of green-only targets. Let's see, so the next thing we've been working on this year is some machine learning to do some object detection on the field. You can see the image here. It's an animated output of our code running on one of the kickoff videos. This is one of their drone videos they flew across the field. We're able to run basically at camera speed, doing this kind of detection on the field, and we're detecting 37 different type of field objects. So anywhere from the game pieces to random graphics, some tape on the field, things like that. We did this by taking about 1,500 images and labeling roughly 14,000 objects in those images. And we made our data set open source. You can see the link here to our GitHub repo. Or if you want to see more detail about this, check out our website, which is team900.org. And then in the labs subdirectory, or the labs link, will be a link to all of our white papers from this year. And so uses for vision data. I mean, getting vision running is cool, but unless you can actually use it for something, it's kind of a lost cause. So this year we're using it, I think, like a lot of teams, for automating our shooter. We have a turreted shooter with a hood. So we use the results from the retroreflective tape to figure out the angle to point the turret and then how fast to run the shooter to hit the right distance that we're at. We're also using the results from vision to localize ourselves on the field. So we take the results from either retroreflective tape or from the object detection code, and we combine that with a map of the known locations of things on the field, and then plus a history of the location of the robot, and we can use that to figure out where we are currently on the field. And you can see that demo in the lower right-hand corner here, where the image on the right with the moving squares is kind of a simulation. The big red square is the robot, and then the red, green, and blue smaller squares are our vision targets we placed in the field. And the image in the left is showing the outputs of our localization code running. So as it moves around, it uses the camera data to figure out where we are in the field and give us a pretty accurate position relative to those known targets.
So now we have Lyra.
Hi, I'm Lyra, and when I was on Team 1678 in 2017, I wrote a vision program. It wasn't especially complicated, but it was very accurate and very reliable. I believe it was one of the only systems that was known to work both indoors and in sunlight. Our setup is very similar to what Anthony described. We get blobs of bright color and do some processing on them to find out which one is the target. The key to this, though, is to apply a lot of different filters. There's several different ways you could use to describe an object. You could describe color, its shape, its position, and in some of those characteristics, the target is quite similar to other objects, and you would have to strike a balance between filtering out things that are the target and not filtering out things that aren't the target. And if you filter with more different characteristics, then you don't have to do that, because you can get a more well-defined area of shapes, and because of that, it's better to write your filters that will keep the target in than ones that will reject everything that isn't the target but might reject the target as well. So we have multiple different filters. We mentioned the first one we do is we filter by color. The target has to be very bright. For us, even on the minimum camera brightness, the target was still sometimes so washed out that it was white. So keep that in mind as well. The target isn't very small. Anything very small is noise, and anything very large is probably glare off of something that is close by. And the target has to be a certain location and shape. The way that you should measure the location and shape isn't by just tuning values. Don't say that, okay, this looks vaguely rectangular. You know exactly where the target is in space. You know how high up it is. And since you know the angle to the base of the target, because you can get that from camera data, you can use that to calculate how far you are if the object is in fact a target. And the same goes the other way. You can use that information to calculate where the top of the target should be given the base of the target. And if the calculated top of the target and the actual top of the target are close to each other, then there's a good chance it's a target. But if they're completely far apart, then it isn't the target. If the target is askew, then you can also use the X position as well as the Y position in the camera. That gets a little more complicated, but it shouldn't be too much more complicated. One thing that doesn't get mentioned enough when discussing how to implement a computer vision system is what to do once you actually get that position data. There's a temptation to say, okay, we have a decent frame rate, we can use this as just another sensor, use it for feedback on our PID loops, but that doesn't work very well. There are a few differences that make a camera meaningfully different from other sensors. It has a higher noise, it has a lower sample rate, and higher latency. Those last two are a big problem because PID loop has a certain frequency, and if the noise or the lag is high enough, it can induce resonance in your PID loop. This is bad, and I ran some calculations on how much lag there would actually have to be to cause problems, and as little as 5% of the period of the PID loop starts to get a major hit in performance, and after around 8% or so, your PID loop is useless. It does nothing. So running feedback off of purely the camera data is a bad idea. What we do instead is we timestamp each image that we get from the camera, so we don't use it directly as feedback. We use other sensors like encoders or a gyroscope to actually run our feedback loops. Then once we get the timestamped image data from the coprocessor, we maintain a history of what position the robot was at, and then we look up what position the robot was at the time that this picture was taken, before all the processing, before everything was sent across the network. And then we look up what the position was at that time and use the data at that time to calculate where we should be, because the camera says we should turn this much. If we've moved since the image was taken, our answer would be incorrect, so we have to use the old value to know where we actually want to go. And then we just run a motion profile or feedback loop off of our encoder data, and then take another picture afterwards to check that we're in the right place. If you want to see how we implemented this, I put a link to a GitHub that actually implements this algorithm on the screen, And if you want to email me, you can also use the email in there. Although if you have questions, ask them in chat.
Yeah, so now let's open up the discussion to the audience. And if the audience has any questions, feel free to ask our panelists. Leave it in the YouTube chat section, and I'll relay those back to our panelists. All right. So in the meantime, how about you guys answer, should your team use like a pre-built solution such as a Limelight, or use a custom vision solution?
So my team has put some thought into this actually recently. In previous years, we'd had students that were very interested in implementing a custom vision solution like the ones we're describing here. And that worked out very well for us. But as time goes on, we've been getting, this year we've gotten a student that's not super interested in vision, but interested in the other aspects of programming the robot. And so we've decided to try using the Limelight in some capacity and see if it works for our needs. And if it does, then to use it, because then the student can focus their attentions on other parts of the code. But because we have the mentor support to do custom vision solutions, it often works out very nicely because we can do whatever we want with changing the exposure and whatnot.
All right, and your comments on the topic, Lyra and Kevin?
Yeah, we have kind of a similar approach where we have enough students who are interested in doing vision code that we can put the resources to it to make it work. I think for a team who is just starting out with vision, especially given how good some of the prepackaged options are now, it may make sense to start with those just to get a feel for what's even possible. Maybe use it as a learning opportunity. It's a small, well, I don't know, small is relative, but it's an investment to actually get like a Limelight in the lab to work on it. But I think just having one in your hands to play with it and see what the options are would give you an opportunity to figure out if this is something you want to really dig into and learn a lot more about, or if it's something where you just want to put it on the robot, check a few boxes, wire it up, and move on to software that actually helps win matches.
And Lyra?
I'll admit that I have not worked with a Limelight or similar system, but for us to get a vision system to the accuracy that we desired, we found it extremely helpful to implement methods that was specific to the target that we were detecting, like the characteristics of, in 2017, there were two targets, one above the other, and we looked at both of them to see, is their relative position correct, that this can actually be a target. And for us, the fact that there were two objects of very similar size in a very similar place indicated to us that a lot of pre-made systems would have trouble dealing with that.
Yeah. So you mentioned that the shape of certain targets are important in code. So can you provide some concrete examples of how you would describe those shapes?
Yes. So in 2017, the targets were two bands of retroreflective tape. So we used one band. So we took one band as the. Sorry, let me explain this again. We calculated the position of the robot based on each of the bands independently. Just saying, given this angle, what's our distance from it using only this? And if the positions from those two values agreed with each other, then we said, okay, this is the target. And if they didn't, then we said, okay, this isn't the target.
All right. And so for all the panelists, what's the importance of vision like to win? Like, how needed is it to become a successful team, and its influence on a winning team?
Well, I think the simplest answer is humans are bad at aiming robots. You don't have a first-person view of what you're doing, and they often require very precise distances and angles.
Anything to expand on that, Kevin and Anthony?
Yeah, I'll come at it in slightly a different direction. So I think a vision system is not going to make a robot that can't aim any better. So, for example, if you have a turret and you're shooting at something, and you set it up and you line it up perfectly by hand, and you shoot 10 balls and only 3 go in, a vision system is probably not going to help you at that point. That's maybe an example of where you should focus on mechanical or something more. But at some point, you're getting to the point where you're hitting 80 or 90% of the shots, and that's when exactly a vision system will help speed things up tremendously. But I think pretty much every team has to make that decision for themselves. Are we at the point where we can just about hit 1 ball out of 5, or do we hit 5 out of 5? We just need to move quicker. I think everybody is somewhere along that continuum, and being honest with yourself is going to probably the right way to evaluate that question.
Yeah. And so for introductory teams, how would we what's a good starting point for a vision code? Because some of the processes that were shown, you said that using limelight is a good way to get started, but what are some other concepts that teams can use to start off?
I guess
if you sorry, go ahead. Oh. All right. If you're just thinking about how to get started with figuring out how to do image processing, certainly just getting the thresholding and the filtering working so that you can just see the target itself, and then for example, OpenCV has a convex hull function, so you can get you can fill in a contour of the target. So it's just this big convex blob, so there's no interior spaces, and you can just find the center of it. And so if you're just getting started and just trying to figure out what you can do vision processing wise, you could just find the center of the target and report it. That's like the basic thing. Then once you do that, you can start trying to calculate distances and do control loops with it. But if you're just getting started, just finding the target is a very good starting.
And
yeah.
so
the other thing, if I can throw something in real quick, which is I think all of us kind of explain basically the same process for retroreflective tape targeting, with some minor variations between teams. But I think a new team starting out could really benefit by learning from what other people did, either by looking at code or looking at white papers, which I'll toss out there because we have several that are available. But I don't think reinventing the wheel at this point for retroreflective tape targeting is really going to be a benefit. There's a lot of things out there you can learn from other teams and not have to take the 3 or 4 seasons to make all the mistakes that they did to learn from them.
So one of those differences in your guys' processes was that Kevin and Anthony, you guys both use dilate and erode transforms, but Lyra didn't. So what was your thoughts behind choosing those transformations?
I'm sorry, could you repeat what kind of transforms?
Dilate and erode transforms.
Oh, the morphological operators?
Yeah.
Yeah, so I mentioned it on my slides, but I didn't say it during the presentation. If you want to get rid of little speckly noise, one way to do it is to blur the image, and then it sort of evens everything out, and because the targets are large, flat planes of color, you can still see them even though it's all blurred. The problem with blur kernels is that they're slow. They have to operate on many, many pixels across the entire image, and so it's difficult to get them to run in real time. So the advantage of morphological operators is that once you have it thresholded, morphological operators are extremely fast by comparison, and so you can get rid of this tiny little speckly noise stuff that happens to be green enough and bright enough to match your threshold, and you can get rid of it with these morphological operators. It's also very simple to sort of understand how it works. If you get into the details of exactly how it functions, it's pretty simple. So.
And then Kevin and Lyra, your thoughts?
The way we also had to deal with the small specks of color as well. And the way we dealt with that was just going through the list, and anything with a very small bounding box just pulled out of the list and got rid of. And the reason we did that instead of the morphological transforms is that our LED was so bright that even on the minimum brightness, it was white. So our threshold had to go all the way to pure white, which means our noise specs were larger. There weren't very many of them, but they were large enough that a dilate and a road to get rid of those would also get rid of the target if it was far enough away.
All right. Kevin?
Yeah, so we have that in there from past years. I think it's probably a really good point that, especially this year where a lot of teams are shooting from a fairly long distance, that it's possible to unfortunately dilate and erode away part of the actual target if it's a really, especially with an angled target, I could see that happening. So I'll say that our code still does have that in there, but I'm probably going to take it to go back and try it out and disable it and see if that helps us detect things better at long distances.
And so, what are some cameras that your teams use for their vision systems? Like some recommendations to get started, like what cameras would you consider buying?
I mean, USB webcams are a cheap, easy way to start. They just work. You plug them in and they function. My team uses essentially USB webcam, except that it does have, it's PCB mounted. It's not like a piece of consumer electronics. And that allows us to have interchangeable lenses, which I briefly mentioned. You can have different lenses for different distances. So, for example, in 2019, where we had a turret and we were looking to the side a lot so we could turn around and engage the target, we had a very wide angle lens. But for this year, we're shooting from a very long distance, and so we've changed out for a different focal length that lets us see the target better but have a smaller field of view.
All right. And then Kevin and Lyra?
Yeah, I'll agree that there are a ton of webcams out there that are just plug and play, and if you're just starting out, that's probably a relatively low, it's a low cost, easy way to get started. I don't know. I wouldn't necessarily recommend the camera we use as a first attempt, but if you find that you want to try something a little bit more unusual, we've been happy with the Stereo Labs products. They're really, it is really nice to be able to get a distance to every pixel on the field that you can see. It makes the calculations a lot easier. You don't have to guess what the height might be or, and back out the distance. You just get the value as a pixel value. So that's really helpful. And then if you decide to go with something like a Limelight, your choice is kind of made for you. You get a camera with that. So that would be another decision you could make.
We used a USB webcam as well. I don't know exactly what model it was. I don't remember, but I don't think it was a super high-end product. You don't need HD streams to get good data from these. A cheap solution works well.
So we had some.
If I can jump in there, yeah, I think the highest resolution we've ever run on the field is, we call it 360p. It's basically like a widescreen VGA. So you really don't need incredible resolution to be doing the kind of processing we're talking about here. You don't need like a 1080p or 4K camera to have an effective vision system.
Yeah. So building on that, there's an audience question asking, what kind of characteristics do you look for in the cameras that you use?
It's important usually for these cameras to be able to adjust the exposure, because like Lyra was saying, the targets can get washed out where they look white even though they're very bright green, and so lowering exposure almost to basically for every camera we've used, we lower it to the lowest possible setting. And some cameras are kind of stingy about allowing you to do that. So you might have to find a couple, try a couple before you find one that lets you. Yeah, I literally just exposure settings and then possibly some color funny business when you, especially when you get to low exposures. We've sometimes had a little bit of a problem, but generally it's okay.
To piggyback onto that, if a setting says that you can change brightness, that typically isn't the same thing as exposure. It just takes everything down a notch after the picture is taken, and you lose that data.
Then Kevin, do you have any characteristics that you'd look for in a camera?
I think I hit everything that we would look for. The exposure is really probably the biggest thing you would care about. If you can get higher frame rates, sometimes that would be nice. So a lot of standard webcams run at 30 frames a second. If you can run it faster and your system can handle that, that might be a useful feature to have. But it's way lower in priority than being able to get the exposure right, because if you can't get that, you're not going to see anything at all useful on the field.
Mm-hmm. So Kevin and Anthony, you guys mentioned using Jetsons. So there's a question asking, for teams that don't use the Limelight and are using Jetsons, how do you harden them to become more reliable on an FRC robot?
I can answer this. So my team, I mentioned we use an Orbity Carrier board, which the one that the Jetson TX1 comes with, the carrier board that holds the processor and everything, is like this big. Let's see if I can get my fingers in frame. It's huge, but it's flat, and so we bought the Orbity Carrier, which makes it more like a box instead of a big flat plate, which helps it to take up less space to minimize footprint. But we also 3D printed a case for it. So if you have a 3D printer available, I would definitely recommend doing so, because it protects electronics from metal chips and other random crap. As far as power is concerned, let's see, the Jetson takes 12 volts. No, it doesn't. It takes it from a range of voltages, actually. That I believe it has a power supply on it, but I might be wrong about that. But regulated power is available from the VRM, and if it works with the Jetson, I would recommend using it.
Okay. Yeah, we do a lot of the same things. We used the TX2 last year, which is basically the same form as the TX1. The giant, 8-inch by 8-inch PCB that doesn't fit anywhere. So we used a slightly different carrier board. For us, it was an Orbity J120, which is basically the same size as the Jetson heatsink module. It just makes it a little bit deeper. So the same thing Anthony was talking about. A case we found was very important. Aside from metal shavings, which are an issue, it also keeps things like game pieces from hitting your USB connections. As much as you can put inside the case and just have wires coming out, so even not having connectors exposed is nice. For the power supply, we actually ran a buck boost converter to do DC to DC conversion. It did a really good job of smoothing the power out, and then we could run it off a regular PDP slot that way. So we had problems where if the robot drove too hard or we turned the LEDs on and off, we could reset the Jetson. Adding the buck boost converter fixed that problem pretty much completely.
I forgot to mention, actually, and it sort of falls into this category. You have to set up your Jetson so that when the thing turns on, it launches your vision application. We never mentioned it, but that's very important to have a script that auto restarts in case of a program crash or whatever, because some random stuff will happen on the robot, or your power will fail, or something weird will happen, and then the Jetson turns off and it turns back on, and you have no vision. I just thought I'd mention that as a minor note.
Yeah. And so another audience question. As panelists, what are your thoughts on using software like Grip, Photon Vision, or Chameleon Vision?
Okay, so I saw this audience question and I Googled those three things because I'd never heard of them. All right, so as far as I can tell, Grip is like a GUI-based application that generates some OpenCV code. So, I mean, I'm all for having this program that sort of shows you what's going to happen before you implement it. This seems like a great way to sort of feel your way around it first. And then when you're done, presumably you can export this to some code that you can run on the Jetson. Like I said, I've literally never heard of this before now, but it looks fantastic. You can figure out if your pipeline works before you have to put it on the Jetson and try to get it through the robot. So Photon Vision appears to use Solve PNP, which I have heard of before. So Solve PNP is a thing that OpenCV has a function to do. Solve PNP tries to figure out the robot's pose, which is the orientation and location, based on a target that it knows the size and shape of, and so it's super powerful. We tried to do it recently, and what we found was that without much higher resolution than what we have, we had a lot of trouble with finicky results. So, for example, Kevin was saying that he's using 360p, right? And we use, I think, 480 or something like that. But if you want to do Solve PNP, you got to go higher. But it's definitely like super cool because you just look at the target and you know where you are. It's like the best of all worlds. So, but again, I don't really know much more about it than that. So I mean, these softwares all look great. They look like they help you in programming up your vision stuff. Looks good. To answer the question.
And then another audience question: is there a reason to use network tables, or are there other alternatives to transferring information from a vision system to a robot?
Let's see, we've experimented with using network tables in the past. We didn't settle on using it just because there were other options that made more sense for us. From what I understand, that network tables will build for pretty much any coprocessor that you want to run it on. So it'll work on the Jetson, it'll work on a Raspberry Pi. That would probably be the lowest barrier to entry for people. It's something that's familiar and useful and works for them. In the past, we've used something called ZeroMQ, which is a really lightweight networking application that lets us transfer data over. And I think Anthony mentioned it, but we're doing something very similar where we're transferring the minimum amount of data from the Jetson we need to. So instead of transferring the whole image over, we're really just giving targeting information. Like, here's a target, here's the coordinates of it. So it's a very small amount of data. If you're transferring whole images, then I think the idea of using something like GStreamer or some of the things provided with the WPI lib would be useful there. We're more familiar with GStreamer just because we use it, but I know that, well, at least I've seen references to WPI lib adding stuff to their Raspberry Pi image to make this a fairly straightforward process also.
We used UDP messages. We bundled up vision data in a protobuf structure and serialized that to send across the network. But it doesn't even need to be that fancy. If you're just sending angle and position and then a Boolean whether it's found, you can just send a handful of bytes. All you need is the known format.
Yeah, Code Orange also just used UDP sockets. We sent a number of angle and distance chunks, one for each target we found in 2019, which sometimes you could see more than one. And then on the Roborio, we'd select one based on distance and some other criteria. And then, like Kevin said, we used GStreamer to encode it. So that makes it a lot easier to send it within the bandwidth limit because, when you're doing vision, most of the frame is black. And so the H.265 encoder can really crunch it down to basically nothing, and so you can skate in under the bandwidth limit.
Isn't the bandwidth limit just for the Wi-Fi? If you send something just from a coprocessor to the Roborio without it going across the Wi-Fi, does that go towards your bandwidth limit at all?
I don't think so. No, I was talking about streaming to the driver station specifically.
Oh,
if you want to
okay.
just store it on the Roborio,
Okay.
yeah, no, that's no problem.
Okay.
And then another question is, how did, as panelists, how did you solve the issues of having bright green lights and keeping robot inspectors happy? I know, like, the light might personally hurt my eyes.
Yeah, so on Code Orange, our bright green LEDs, like I said, we use a what the heck did I write? Exactly. We use a constant current driver we bought from Adafruit, I believe, and it has a pin to enable and disable it. So it was super cheap. It was like $10 or something, and you can just hook up the enable disable pin to the Roborio and use a digital input output. I forget exactly how we implemented it, but if you do it with a relay versus a DIO, you can get it to turn off when the robot boots immediately, which is nice so that you don't blind people when you turn it on. But other than that, yeah, just hook it up to the Roborio and you can enable disable it. That's the easiest way I can think of to do that.
We also had a switch on it so we could turn it on for the field and off for moving it around and inspections. So again, we wouldn't blind people.
Okay, yeah, the zebra corns are a little bit unusual, so we basically just threw a cloth over it when it was in the pits, so it wouldn't blind people. But more seriously, we printed up a 3D printed case for the camera that has a recessed place for the LEDs to go in, and we can recess them a little further back so it still points at the target but doesn't blind people off to the sides, so that does help a little bit. And then we also had an implementation of hooking up to a GPIO, or I guess a DIO in this case, being able to shut it off as we needed to.
Yeah, we got a little fancy and had it only turn on when we were actually tracking the target, which was nice. But yeah, you can be a lot simpler than that.
Yeah. And so, what's a good language to write your vision code in? I know it varies depending on the team, so panelists' thoughts on that?
We used C++. I believe a lot of languages work with OpenCV, but most bindings are written in C, so C and C++ are just easily compatible with everything.
I mean, there's something to be said for language compatibility. So you might want to, if you're writing your robot code in Java, you'd want to write your, or even just programming knowledge. If you're writing your robot code in Java, then it might be nice to write it in Java, your vision code in Java. However, C++ has a definite performance advantage over Java. So if you're running into performance issues, that is a way to improve it, is to switch to C++. We've had programmers, luckily, that are experienced in C++ or have been able to learn it in a fairly short period of time, so that wasn't a big deal. Java and C++ are both object-oriented, so there are definite differences, but they're not wholly dissimilar. So, yeah. We wrote ours in C++, just for reference.
Yeah, most of our code is in C++. We do have some in Python, which is also another binding that supports OpenCV. And for us, we use it because it's also useful for TensorFlow, which lets us do some AI stuff. The big advantage we found from Python is rapid prototyping is really rapid. So a lot of the vision stuff, you'll get something together, get a pipeline idea in your head, and it's really nice to be able to quickly test it and see if it works or not. And then Python is a good prototyping language for that because it's really quick. You don't have to compile. You're not debugging out-of-memory pointer errors like you could in C++. But that being said, the majority of our code is in C++.
Mm-hmm. And so, on your guys' respective teams, what do you guys look for inspiration with your vision systems? Like other teams or other groups or things when you're, fixing and producing these vision systems?
Yeah, I know for us, one of the things that was really helpful early on was 254 put together a talk at Champs that laid out a lot of some of the more detailed things that we'd seen and we knew kind of how to fix, but not really why fixing them helped. So things like why does the target turn like this kind of blue-green teal color if your exposure is wrong? They were able to explain that in a lot of detail that made a lot of sense. So looking at that presentation helped. And then just seeing what other teams are capable of, watching what happens on Champs or, even, regional championship matches, seeing what we can get inspired by from there. Maybe we want to try and make a robot do that or, ooh, we're close. We could almost do that. Let's make it work. That's really nice to see.
I mean, 971 is always fun to watch because they have some very good control going on. But 254 has done some impressive stuff. Let's see, which year was it? It was 2016 that they had their vision system was running off an Android phone, and they had tracked the goal so well that they were strafing left to right and were able to point at it basically constantly, and it was very impressive to see. Just like Kevin said, just see what other people are doing, see if they do some cool or interesting stuff. I learned some stuff from listening to your guys' talks about it, doing the machine learning and stuff. So yeah.
For us, we looked at talks and published code from 971 and 254, but our biggest source of documentation was just the OpenCV tutorials themselves. I think they're very well written and easy to understand.
So we have time for 2 more questions. So if the audience has any more questions, please put them in the chat right now. And we should be wrapping up very soon. If you guys have more questions afterwards, the panelists' contact information should be on the Capital City Classic website, and these videos will be put on YouTube, so you can watch it later and for the contact information through there as well. Well, in the meantime, how about we answer this question? Do you need a coprocessor, or can you simply run vision code through the Roborio?
I mean, you can run stuff on the Roborio. I've seen some projects that do that. The only one that I believe I saw that was working at a decent amount of, or working at a decent efficiency so that you can get a high enough frame rate was something that was using some assembly stuff. The Roborio doesn't have a whole lot of processing power, and the Jetson has a graphics card in it. It is made to do parallel processing, so it's super fast at doing these things. OpenCV has connections for NVIDIA CUDA stuff. It can access the graphics card at a very intricate level. The Roborio is a processor, like a regular CPU. It can do the vision processing, it's just a lot slower. So yes, and also Code Orange actually, when we first started doing vision, was running vision processing on our driver laptop. So we would send the frames over Wi-Fi and then process them on the driver laptop and then send that information back to the Roborio. That introduced a huge amount of lag, which we had to deal with in the control loop. But it ended up working out. So if you really can't deal with the coprocessor and your laptop is somewhat powerful, you can try to do that. But I really wouldn't recommend using the Roborio because it's got a lot of other stuff to do and can't really handle the vision computations.
If you do vision on the Roborio, I mean, I mentioned how to deal with latency, but you also have to worry about bleeding performance away from more important tasks if you're doing that on the Roborio. In 2014, there were goals, and one of them would be highlighted for extra points, and this would be before the match. So to score that autonomously, what we did was we did just use the driver station to run vision, but that was because we only needed one picture to process.
Yeah. One thing I'll mention, from what I feel bad saying this because I haven't actually used one, but my understanding is the Limelight is essentially a coprocessor and a camera combined into one that you can just kind of buy off the shelf. So that kind of gets you the benefit of having a coprocessor where you're not taxing the Rio or having to really run it, beat it up to make it work. But at the same time, you don't have all the downsides of getting a coprocessor working, like we talked about, the power supply and how do you transfer data back and forth. All that's handled for you. So again, that's kind of pointing towards, as a team who wants to know if they should use a coprocessor or not, maybe a Limelight or something similar as a way to start, like kind of an in-between step there and see if it's what they really want to do.
A big thank you to our panelists. Thank you for coming to this workshop. I believe we have another workshop after this, or yeah, CCC should have another workshop after this. But thank you to our panelists. Big thank you there.
Yeah.
Yeah, thanks for having us.